Okay, and welcome to this next tutorial. In our final tutorial, we will begin to simplify trigonometric expressions. Okay, so if you'd flip over to example 2, we're going to begin simplifying our trig expressions. Okay, guys, here's the deal. We are beginning a journey that will be about 3 blocks long. The reason why we take a while with this topic is because there is not just one particular set of steps to follow. There is not a process to follow. What I will do is show you many different situations and scenarios and show you some strategies that will work in those situations. You will learn this topic only through practice and exposure to these various situations. There is not just one way to solve each of these. In many cases, there are multiple paths to take. You might take 5 steps to solve where your partner might need 7 steps. As long as you both get to the same final answer, it doesn't matter how long you take. So some of you will catch on to this from the beginning. Many of you will need some more practice before it really clicks with you, and that's fine. My simple hint is this: the ones that will have the fastest success with this are the ones who honestly are reviewing their flashcards on a daily basis. Those students will simply begin to see things quicker than other students. Okay, so let's begin with this one. I'm going to show you 2 different paths, although everybody's first step is most likely going to be the same. The first identities I always look for to substitute out are the cofunction identities and the even odds. And I see an even odd identity happening right here. I have this, I know this because I've got the negative angle, and none of the other trig functions have a negative angle, so I want to get rid of that. I need to remember which one of the functions, even or odd, the sign is. And this is one that I remember because I know that the sign changes. That's sort of a little hint that I use in my brain for the even odds. The sign, S-I-N-E, its sign, S-I-G-N, will change. So the sign changes. So when I change this, it's going to become the negative sign of x, which actually changes this positive. So that's going to be my first step. This will become negative sine of x. Okay, so now I'm going to branch off and I'm going to show you 2 different versions, 2 different paths. I'm not suggesting you need to find as many paths as possible, you just need to find one, but like I said, I want to expose you to a couple different paths. The first path, I'm going to call it the Pythagorean path. A lot of people are going to start to fall in love with the Pythagorean identities because you're going to see that we use them so often. I'm just going to rewrite the problem over here. I've got sine x times cosine squared x minus sine x. Obviously, we've got something that's being squared. And if we have something that's being squared, we can replace it with one of the Pythagoreans. And if you look at your Pythagorean list, the cosine squared is equal to 1 minus sine squared. So I'm going to substitute cosine squared away and put 1 minus sine squared in its place. Whenever I substitute, especially with a binomial, I put that in parentheses. Okay. Now since I have some parentheses, distribution makes sense. I'm going to do sine x times 1. I'm going to do sine x times negative sine squared. That would make negative sine cubed x. And then this is still minus sine x. I've got this expression here, and now I've got a positive sine x and a negative sine x, so those 2 terms will cancel away, and I'm left with negative sine cubed, and that's as simplified as we can get. I call this the Pythagorean path because I saw something squared, and I wanted to use a Pythagorean identity to replace it. And then I just did some simple algebra steps, distribution, and combining like terms. So maybe you saw that. Over here, I'm going to call it the GCF path because when you see the sine x cosine squared, I'm going to rewrite the problem over here, minus sine x, some people might be saying, well, wait a minute, I see that both of these terms, this first term and the second term, share a sine x. So why don't I factor that sine x out as a GCF? If I divide that sine x away from both of the terms, I'd be left with cosine squared, and then the minus, and then 1 left right there. So I've got sine x times the quantity cosine squared minus 1. So now we're looking at this. Some people are saying, well, wait a minute, I know cosine squared minus 1. I've seen that before. But no, you actually haven't. On your flashcard or on your list of identities, what you see is 1 minus cosine squared. And there's a big difference between 1 minus cosine squared and cosine squared minus 1, because they are not the same things. In fact, they would be opposites. If you take any two numbers and subtract them, let's say 1 minus 5, you get negative 4. If you switch that around and say 5 minus 1, you get positive 4. Whenever you flip around a minus sign, you have the exact opposite. And this is the exact opposite of what we're supposed to have, which means that when we do replace it, we should have the opposite of what we thought it would have been. So cosine squared minus 1 is negative sine squared, because 1 minus cosine squared, the proper order, is equal to positive sine squared. If I flip around the minus sign, I get negative sine squared. And now that I've got sine x times negative sine squared, I've got negative sine cubed, and we got it in the same amount of steps. The question is, which way will you see when you see a problem like this again? Will you just go straight to the Pythagorean path, distribute and combine your like terms, or would you see a GCF and factor it that way? You're still kind of using a Pythagorean, the opposite. Let's look at our next problem. I'm using alpha this time. The first thing I see, almost everybody's going to do this as their first step. Again, I see this pi over 2 minus alpha. That's one of our cofunctions, and the sign of that will be replaced by the cosine of alpha. All I do is I put the co on. So I've got sine of alpha plus I've got cotangent alpha, and then the sign of this pi over 2 minus alpha becomes cosine of alpha because that's a cofunction. So now we're looking at this, and unlike the last problem, I don't have a GCF to factor out, and I don't have a Pythagorean. I don't see anything squared yet, so I'm kind of stuck right now. So I'm going to use that strategy that we talked about and change everything to sines and cosines. I don't like that this cotangent is here, and I've got another name for cotangent, so I'm going to replace cotangent with cosine over sine, since that's what it's equal to. And I'm going to multiply that to this cosine. Actually, I'm going to put that over 1. That might help me to multiply these two fractions. Let's multiply the fractions together. Multiplying fractions is pretty simple. We multiply the numerators and get cosine squared. Multiply the denominators and we get sine. So now we're looking at this. Now I'm going to branch off into two different paths again. Again, just to show you different ways. This one, I'll call this combining fractions, because some people say, okay, well, I've got these two fractions. How about I just get a common denominator and combine these two fractions? Okay, so we've got the sine, maybe I put it over 1, plus the cosine squared over sine. To be able to add fractions, you need to have the same denominator. So since the denominator needs to be a sine, I'm going to multiply this denominator by sine and the numerator by sine. So I'll multiply by sine over sine. Now I'll have sine squared over sine plus cosine squared over sine. Now that they have the same denominators, I can combine these two fractions together into one that share that same denominator, and it would be sine squared plus cosine squared. And hopefully you see that's one of your main Pythagoreans. Sine squared plus cosine squared will always be equal to 1. So the numerator simply becomes 1. And the denominator, of course, is still 1 over, it's sine, so 1 over sine, and 1 over sine becomes cosecant. So combine the fractions together, get your common denominator, see what happens once it's combined, and we actually will use the Pythagorean there to make that equal to 1. The second path over here, I was actually going to call the Pythagorean path. Because I see something squared again, and maybe that's going to help me if I use a Pythagorean. Cosine squared over sine. I see this numerator, this cosine squared. In fact, I think we've dealt with cosine squared before. In the last problem, I'm going to replace that numerator with 1 minus sine squared. That's one of our Pythagoreans. And now we're down to this. Now I'm actually going to split the fraction apart. I have a binomial in the numerator and a monomial in the denominator, which means that I can split this fraction into two different fractions. Here's my sine of alpha, of course. This first fraction is just 1 over the sine, minus the second fraction is sine squared over sine. For the same reason over here that I can combine these two fractions together because they have the same denominator and get this purple quantity, I could split them up into two different ones if I wanted to. And that's what I'm going to do here. Some people call this the butterfly or the pretzel because it kind of looks like a pretzel. That's fine. Split them up into two different things. Now I've got the sine. I know that this is equal to cosecant, which I know is going to be the answer. And here, I've got sine squared over sine. One of these factors can cancel with one of these factors, leaving just sine alpha in the numerator. And then I see my like terms. They will cancel away. And then I'm left with cosecant. So again, two very different paths, and yet we both got to the same answer. The question is, which path will you see the next time you see a problem like this? Let's go to our final problem. In this situation, I have two fractions, and I'm going to use the combining fractions route. I'm going to give them the same denominator and combine these fractions and see where I am. So one of the factors in the denominator is 1 plus cosine, and since this fraction doesn't have that, I'm going to give the 1 plus cosine factor to the top and the bottom. This other factor in the other fraction is sine, and since this one doesn't have a sign, I'm going to give this fraction the sign. Put that in parentheses, I guess. So I'm multiplying this fraction by sine over sine, and I'm multiplying this fraction by 1 plus cosine over 1 plus cosine. Let's see what happens here. The numerator up here is going to be sine squared. The denominator is going to be, I'm just going to leave it as sine times 1 plus cosine for right now. Typically, I like to leave things in factored form until I know that I should distribute. I leave them in factored form because sometimes the factors will cancel away. And I don't know if they're going to do that or not until I get to that step. So let's see. Sine and 1 plus cosine, I'll leave that, like I said, in factored form. The numerator, I'll go ahead and distribute. Cosine times 1 and cosine times cosine becomes cosine squared. So now that these are the same denominators, I'm going to combine them together. The denominator, of course, stays the same, and the numerator becomes sine squared plus cosine plus cosine squared. Okay, so now we've combined the fractions into one. Do you see what I'm going to do next? Do you see that main Pythagorean? I always love to see sine squared plus cosine squared. I don't care that there's a term in the middle. It doesn't matter. I can move these terms around. Sine squared, I can put them in whatever order. Sine squared plus cosine squared does equal 1. So now I've got 1 plus cosine for the numerator. And in the denominator, again, I'm leaving it in factored form, and you're about to see why. Because now I can cancel out a common factor. I know that 1 plus cosine is a factor in the denominator because it's being multiplied, and 1 plus cosine must be a factor in the numerator because it's the only thing there. This whole factor can cancel out with this whole factor, and I'm left with a 1 in the numerator and a sign in the denominator, and that, of course, again, is equal to cosecant. So this strategy, actually I only took the one path, but please hear me when I'm talking about this denominator. When I get the common denominator, I leave them in factored form. I'm going to leave them in factored form because sometimes that factor will cancel away. When you get to a point where you realize that the factor is not going to cancel away, then maybe we would distribute. But I leave it in factored form just in case it's going to cancel away. So those are the three problems. We're going to practice this first tutorial again in class. And please make sure you have your flashcards with you in class and study them a couple times. Thanks a lot. We'll see you.